Okay, Year 12, I'm going to quickly go over approximating roots and have a go at some of the questions involved in exercise 9.1, or sorry, 9.2, and some HSC questions. So approximating roots is when we have an equation and we're finding it hard to find where this equation cuts the x-axis or its solution when it's equal to 0, or indeed its root. So as we can see here we have some polynomials, or some functions, and they're crossing between 2 points, A and B. And we're trying to work out, well, where is the root nearest to? And it's somewhere between A and B, and obviously the first guess you want to have is that it's halfway between A and B. So what I'm going to do is I'm going to have a look at a question, an HSC question to discuss this. So I'm going to move all the way down here, and here's a question from 2010. And it says, show that there's a solution to that equation. And I couldn't solve that equation. Well, I don't think I could solve that equation, but they tell me that there's a solution. There should be a solution between 0.6 and 0.7. So the first thing I want to do is I want to go, all right, so I have this equation, x equals e to the minus x squared. And I want to get everything on the same side. So I'm going to bring that e to the minus x squared over. So I'm going to get x minus e to the minus x squared equals 0. And that's what I'm finding the solution to. I'm finding when that equals 0. So I'm going to call f of x minus e to the minus x squared. And I need to show that there is a solution to this. So I'm going to find f of 0.6, and I'll put that into my calculator, and I get 0.6 minus e minus, put the 0.6 in brackets, and note that that negative is outside, squared, and I get negative 0.0976 ... We'll also need to find f of 0.7, and I'll just do the same. 0.7 minus e to the minus 0.7 squared, and when I do that in my calculator, I get 0.08737 ... And that shows that there is a root and that there is a solution. So since f of 0.6 is negative, and you've got to say this, 0.7 is positive, then there is a root between .6 and 0.7, and thus a solution to x minus e to the minus x squared equal to 0, which is what we're trying to solve. So there's your first mark. Now the second mark, by halving the interval. Now I have to find it correct to one decimal place. So let's see how we go. So let's halfway. So let's find f of 0.65. Well, I'll just do that again, 0.65 minus e to the minus bracket 0.65 squared, and that gives me negative 5.4 times 10 to the negative 3. So it's still less than 0. So therefore, it's still negative. So therefore, the root or the solution is between 0.65 and 0.7. Therefore, thus, correct to 1 decimal place well, if it's between 0.65 and 0.7, to 1 decimal place, the solution is 0.7. Now that's an example of halving the interval. Now, in the past, however many years, there's only been one other one that hasn't halving the interval one, and that was in 2005, and there it is there. By halving the interval, find correct to 1 decimal place. Okay, so what do you want to do? You want to develop a different method. Halving the interval is one way. Well, a very powerful mind thought about this, and Isaac Newton came up with a different method. And this is a method we like to use. And here it is. Now, Isaac Newton said, and this generally gives a better approximation, but not in all cases. We're going to see an example of that when we're doing an HSC question. So it generally gives a more accurate one. Now, what did he decide? He said, well, if this is my first approximation, and I find if I find the equation, this is the equation of the tangent at my first approximation, and I find where that equation of the tangent cuts the x-axis. That will give me a better approximation. Now, you can go and look at the proof in your textbook, but suffice to say that when you sub in the equation of the tangent at that first root and put it equal to 0, what you will get as your next root, next one, x2 equals x1 minus f of x1 over f dash of x1. You can go and look that up. Now, I know Margaret uses a here, but your formula sheet uses that form. Your reference sheet uses that, and that's the way that we're going to do it. So let's quickly have a go at some of the ones from the work from the textbook. So we'll go down here and we'll have a go at the very first one. And then we'll have a go. So here we go. Here's a polynomial. Has a root near 2.5. Find by one application. So first of all, I'll change my pen. F of x equals 2x squared minus x minus 9. Well, I know I'm going to have to differentiate this. So that's the first thing I do. 4x minus 1. And I now find, here's my first root. My second approximation. It equals my first approximation, which is 2.5, minus f of 2.5 over f dash of 2.5. So that's 2.5 minus 2 times 2.5 squared minus 2.5 minus 9 over 4 times 2.5 minus 1. And I get 2.38 repeater. And they asked for 2 decimal places, so I'll just go 2.39. Brilliant. Let's have a look at question 5. Now question 5. Here it is. Show that there has a root between those 2 points. Well, first I'm going to write it as an equation. So f of x equals x to the half plus x minus 1. I'm going to quickly derive that. F dash of x equals half x to the minus a half plus 1. Now, I have to show that it has a root between 0 and 1. So f of 0. So originally, f of 0 gives me 0 plus 0 minus 1, which equals minus 1. And f of 1 gives me 1 to the power of a half plus 1 minus 1, which is 1. Therefore, there must be a root for f of x equaling 0 between 0 and 1, because it changes sign. Because here, f of 0 is negative and f of 1 is positive. So it must cross the axis between those 2 points. Righto. Now we'll use Newton's method. So my approximation, did they give me a point? Using 0.5. So we're going to go halfway. So I need 0.5 minus f of 0.5 over f dash of 0.5. So I get 0.5 minus 0.5 to the power of a half plus 0.5 minus 1 over a half 0.5 to the power of minus a half plus 1. And if you put that all in your calculator, you get 0.378679 ... And I think they asked for 3 decimal places, so 0.379 is my approximation. Now that's Newton's method. Remember what it's finding. It's finding the gradient, the equation of the tangent for your first approximation of the root and where that tangent hits the x-axis. And you get the formula on the reference sheet. Now, I could do some more on 9.1, but I want you to have a go at those, 9.2. But I do want to have a look at some of the HSC ones. They do get quite difficult, but in particular, I want to have a look at this one here from 2014. Let's have a look at it. The diagram shows the graph of f of x. They don't even give it to you. They say, hey, we know it has a root at x equals a. The value of x1 is a first approximation. A second approximation is obtained by applying Newton's method using x1. Using the diagram or otherwise explain why x1 is a closer approximation than what you'll get using Newton's method. This is why the understanding is important. If I draw a tangent there, it's going to come down here and it's going to hit there. There's x2. Now x2 is further away from the original root. Here's the original root. That's that. Because Newton's method will not always give. So in this case, you would draw that diagram, you would draw that tangent, and you would say something like, because the equation of the tangent at x1 is negative, the second approximation, you don't need to write all this, it said using the diagram, so we'll use the diagram, using a diagram, so the diagram is enough. The second approximation, but I'm writing it out, using Newton's method, should give Newton a capital N, I think he deserves it. Because the equation 10 is negative, the second approximation using this gives an approximation further away. Further away than the original. Now, you probably didn't need to write all that, but it is vital that you understand what Newton's method is doing. Now, all throughout these, every single time, and you're going to get one in the HSC, it's going to usually involve Newton's method, but every year there is a question on approximating roots. Every year. It is usually using Newton's method. There have only been 2 questions on halving the interval in the last 7 years. And you saw those, one in 2005, one in 2010. It would be unlikely that you will get one on halving the interval, but it may also mean that halving the interval is due for a comeback. Make sure you can do both methods. All right, good luck with those, and